Okay, how are we feeling? Thumbs up if you're good, thumbs down if you would like more time. Okay, I'll give you guys a few more minutes. I realized the last one is really horrible grammar. Ignore that. Just stick, yeah, just you get the idea. Okay, so let's take a look. Okay, cool. Okay, I'm gonna use Data Hub today because maybe that'll be a bit nicer. Okay, so all right, so let's. Oh, I lost it. All right, so let's do the first one. Okay. Why do we need to curve fit data?
To better understand the relationship between our variables.
Good. Good. Yeah. What essentially are we turning data into?
Function.
Good. Yes, exactly. So we're basically, when we fit data, we're trying to do predictions. But yes, it's very good. We're trying to figure out the relationship between all of our variables. This is just one way of doing this. If you want to get more complex, you can take a Bayesian class where they basically figure out all the different probabilities for all the different types of variables in crazy, crazy ways. We're not doing that in this class, but yes, great. Okay, so next question. What arguments do you need to feed scipy.curvefit? Do you guys remember? Yes.
I think it's just x, y, and the type of function that you want, linear, quadratic, cubic, etc.
Good, yes. And then the function. Good. Okay, cool. Is it the other way? Yeah, okay. So we go function, and then we have x data, and then we have y data. Great, perfect. Okay, so you'll also find out today that you can give it initial conditions, which are p naughts. So you'll play around a bit with that today if we get to it. But yes, those are all the arguments to SciPy. Great. Okay. What does popped return and what does pcov return?
I think opt is like the optimal parameters.
Great. And then do you remember what pcov is? Yes. Great. Yes, the covariance matrix. So this is basically this would be like Rm and Rb, and then this would be Rm error, and Rb error. Great. Okay, cool. Next question. How do you plot the line of best fit? Let's say we're just in the linear case. So like if I did plt dot plot, how would I plot my new SciPy function that it gives me? Yeah.
you have like a thing where you break up the tuple of the option points into values and then like those individual values will fit inside the plot.
Great, yeah. Um, that is a totally good way. And then there's also this way where we take our function and then we can take our asterisk and then type popped. And it does the same thing. But yeah, great, great. Good stuff. Okay. Just a couple more questions. How do you figure out the error on your line of best fit? It's that nasty equation I gave you last time, if anyone remembers. Has to do with the covariance matrix. Is okay, I'll just give it to you. So it's np dot square root, and then we do np dot, oops, sorry, np dot square root, and then np dot diag, and then pcov. You don't need to memorize this. You can totally just look it up. Didn't expect you to memorize it, but this is just one way to get the errors. There's more complicated ways, but that's just what I taught yesterday. Okay, great. Now, finally, last question. What is the reduced chi-squared? Why is it helpful? I see the same three hands, but yes.
Does it feel like the closer it is to one, like better?
Yeah, great. The closer to one, the better. Though not always better, because sometimes you might suffer from overfitting. If you don't know what that is, don't worry about it, but it's basically like your function is doing too good of a job and you're over constraining. It's like, you know how that data we had yesterday or Monday where it was like all spread out? Overfitting would be like you're trying to do like a sine wave all the way up and down through all of your different parameters. It's like, while technically that might fit your data better, that is still overfitting, and you want to avoid that as well. It's a tricky balance to play, but anyways, just keep an eye out for it. Okay, great. So those are the warm-up questions. These will be posted later if you want to take a bigger look, but that's just basically a warm-up for today. So let's talk a bit more about Scipy from last time, and then we'll jump into an example with some more real data. If you want to download it, it's under Files in the lecture and demos. It's called spectrum.csv. So you can take a look at it there. But just to recap, so last time we practiced importing data with pandas. When you go to use your own data, I highly recommend using pandas to manipulate it. We'll learn about AstroPy, and some of you might be working with FITS files. And so you'll use AstroPy to import your data, but then I still recommend using pandas. But yeah, so that's what we did yesterday, or sorry, Monday. And then once we had our data, we put a linear fit to it, and then we use the scipy.curveFit function to get out our parameter values that Scipy thinks it is, and then the error on those parameter values. Cool. So, and then we plotted the data. We got this nice line curve. And yeah, that's basically the bones of Scipy. Okay, so now it's time for you to practice. But before we do that, I'm going to give you a bit of background. Funny story. I did have real spectrum data for you to analyze, and I had processed it. But I did that this summer, and then unfortunately I can't find the file on my computer. So what I did instead was I made fake spectrum data. So it's still cool. It still does what we want it to do, but it's not technically real. But next week we'll work with real data for AstroPy, because I do know where that file is. So sorry about that. But anyway, so spectrum data. For those of you who don't know, a spectrum is basically the footprint or the fingerprint of a star or any kind of body that emits light. So if we take our sun, it is something called a black body. You do not need to know what that is, but basically it produces a rainbow of light. So if we take these are all the wavelengths of light, and then from it we get emission spectra, and the sun produces basically a rainbow of emission. And then there's these black absorption lines. This is way beyond what you need to know if you've never taken Astro 7A, but essentially we are going to be looking at emission line spectra today. So basically it's going to be a plot. It's going to be a bunch of data. There's going to be wavelengths of light, and then there are going to be peaks in that data. And those are going to tell us what kind of elements our gas is made out of. Maybe if you've done like 5BL or 5CL, I know there's a bit of emission in there, but this is completely new. Do not worry. It's just data at the end of the day. Okay, so with that, I'm going to first leave you with this. So open a Jupyter notebook. import your 4 favorite functions now. They'll probably be there at the beginning of every notebook. I put a data file called spectrum.csv, import it as a pandas data frame, find the shape, find the rows, find the column names, and then you'll see that the column names are wave and flam. So Google those and let me know what you find out and what they mean. But hint, I already told you what wavelength is. So yes. Okay. Thumbs up if you would like me to go over it. Thumbs down if you would like more time. Can more people vote? Okay, I see a lot of thumbs down. It's for what? Disneyland. It's from Scipy, so it's like from Scipy. Okay, to avoid running out of time, I am gonna get going. But we'll work on it together. So, going back to my data lab. All right, so first, oh wait, actually, give me 1 second. Here, I'll give you a couple more minutes. I need to upload the file. All right, so how do I import NumPy? I call import NumPy. And then I'm going to import matplotlib. So import matplotlib dot pyplot dot pyplot. Oh my gosh. As PLT. And then I'm going to import pandas as PD. And then I'm going to import scipy dot curvefit. Sorry, so from scipy dot optimize. Scipy dot optimize import curve fit. Great. Okay, so my first task for you was to import the file. So can someone tell me how can I import my Spectrum file? Yeah.
Yeah, equals pd dot read, CSV, and then underscore CSV, and then parentheses, quotation spectrum dot CSV.
Great. Cool. And then I'm going to run it. Perfect. All right. So now how do I look at the shape of my data? Great. So let's take a look. Oop, my bad. Cool. So we have how many rows and how many columns? Great. Okay. So now how do I look at the column names? Yeah.
So you do print df.column. If you want it to not be wrong, you do print list df.column.
Good. This is good enough. But yeah, awesome. Great. So for my column names, I have wave and I have flam. So those are my column headers. Perfect. Cool. So now I'm also going to print the first 5 rows just for fun. So df.head. That gives me wave on the left, flam on the right. So I have these larger values, and then I have these really, really small values on the right. Then we can print df.tail just to see what the other side looks like. And great. So these numbers are getting larger, and then these numbers are getting, well, they're just varying a lot. So, okay, cool. All right. Next question. What does wave mean in terms of this? Yeah, perfect. Yep. So in this context, we're looking with spectrum data. So this, the wave, equals the wavelength of the spectrum. So wavelength is another fancy word for color. So we're working with a bunch of different colors and the intensity of those colors in our data. Great. Okay. Now what does flam mean? This one's kind of mean, but I'd love to hear your suggestions. Yes.
It's
Yeah, oh my gosh, too good. So flux per wavelength. So per wavelength. And why it's called flam is because lam stands for lambda, and lambda is a fancy, it's not a fancy, it's a Greek symbol. And it just like looks like this. And like that's commonly denoted for wavelength. So didn't need to know that ahead of time, just a fun fact, but great. Okay, cool. So that is the first step. Did I ask you to do anything else? Great. Okay, so now why are the names of our columns important? It's kind of a loaded question. It harkens back to basically I did this very poorly in terms of naming the column heads. It would be better if I'd written wavelength completely and it didn't use the unit because you have no idea what units we're working with, right? Like you could take a guess, but could be it could be meters, it could be kilometers, it could be like micrometers, so that's kind of bad. So you always want to have good labeling, and then flam, that's not a great title at all. Like unless you like know what lambda is. So come up with like when you're coding and you're coming up with variable names or you're sharing data or you have plots, make sure they're descriptive titles. So little lesson there, but great. Okay, cool. So next question. All right, so now I want you to plot the data with df wave, df flam, add axes labels. I want you to, what do you notice about it once you plot it? And then bonus, the units you're working in is angstroms. You're welcome to Google that. A little bit of a research class, and then try and convert it to nanometers, and try and figure out what regime we're working in. This is all bonus. You don't have to do anything below 3 if you don't want to. But if you'd like an extra challenge, be my guest. Okay, thumbs up. Feeling good? You want me to go over it? Thumbs down. One more time. Please vote, otherwise I don't know. Okay, cool. I see some more thumbs up, so let's go over it. Great. All right. So first thing I ask is plot the data with df wave as your x values. So can someone tell me how to do that?
You can set x equal to spec or df graphics of the kind of wave, and then set y df graphics.
Great. Thank you so much. Perfect. Okay, so there are my x, there are my y. What do I ask you to do next? Okay, so now I want to plot them. So I'll just walk you through how to do this. So we can call plt dot plot, and then I can call x and then y, and then label equals data. Not very specific, but whatever. We can, yeah. Okay, cool. So let's plot that. This is roughly what we get, which is really cool. Remember this is fake, it's not real, so sorry about that. Okay, so now let's add our important information. So we'll add an X label. So our X label, I told you, was the wavelength, but in a unit called angstroms. Angstroms. Cool. It's kind of a more, I don't want to say historical, because I feel like that's kind of mean. But I feel like a lot of wavelengths are now written in nanometer ranges. But, you know, if you're working with more infrared, maybe it's angstroms, but I commonly see it as nanometers. But cool. Okay, and then we have flux, which is lambda. If you've never heard of the word flux before, no worries. It's basically just brightness. So how much of that color, because remember, color is a wavelength. So how much of that color are we getting? So if it's like a red, then like how much red is our star made out of? How much blue is it made out of? Etc. Okay, cool. So now I'll plot a legend because I'm being a good data scientist, and then I'm going to plt dot show. Okay, so here we go. There it is. Let me zoom out a little. There I have my X label, I have my Y label, I have my legend, and then yeah, there we go. Cool. All right. Does anyone else need to copy this down? No? Okay. So, next question. What did I ask you to do? So, yes, what do we notice about the plot and what are its distinguishing features? So, what do people notice about this guy? Yeah. Awesome. Very good. Very good. Okay, what else do we notice? Just kidding, that's it. Okay, so great. Yeah, so there's three peaks. But what we want to do is we basically want to figure out what wavelength this peak is at. So when you do spectroscopy analysis, if you go on to do like optical lab or continue on in astronomy, you'll probably run into spectra. My friend Caitlin, she literally spent an entire summer looking at a single spectrum. So you can do a lot with these guys. They tell you a lot of information. But basically, we want to figure out what this value of emission we're getting. This is beyond the scope of the class. You probably need to take more physics and astronomy to understand. But anyway, these are very relevant for astronomy. Okay, moving on. So, does anyone want to do the bonus? Or do you want me to move on? Take a vote if you want me to do the bonus. Okay, we'll do the bonus. All right. So, convert the y-axis from angstroms to nanometers. Okay, can anyone help me with that? Well, first you need to know what an angstrom is, and you need to know what a nanometer is. But can anyone? Yes. Oh, sorry.
Extra 10 to the negative 8, then nanometers 10 to the negative 9. So either we're dividing by 10 to the negative 8, and then dividing by 10 to the negative 9, so we either multiply by 10 to get there.
Almost. You're very close. But it is an order of 10. So we're going from angstroms. Yes. So we're going from angstroms to nanometers. Unless I'm wrong, you're welcome to correct me anytime. Okay, so we're going to PLT dot plot, and then all we're going to do is we're going to take x, and we're going to divide it by 10, and then we're going to do y. And then we will PLT dot show. And let's look at our y-axis or x-axis. Now we are in nanometer range. So that's all we did, just divided by 10. Yeah. You're welcome to plot it however you want. I personally prefer nanometers, so that's why I plot it in nanometers. Okay, so next question. Does anyone know what range we are working with? What range of spectral data? Just a guess. It's okay if you have no idea. Yes. Boom. Okay, so fun facts from Bree. Well, no. Okay, so your eyes see from 400 to 700 nanometers. So that's called the visible range. Anything below 400, so on this side, like way over here, that's UV. That's like the stuff that gives you skin cancer. And then there's all the infrared, which goes on for a really, really long time, and then you enter it like microwave and radio. So yeah, we're working in the infrared. That doesn't have anything to do with it because it's fake, but you know, it's fun. All right, so moving on. Next question. All right, so this is where it gets more difficult. Now I want you to create something called a mask. You might not know what this is as you're trying to code. No worries, we'll do it together. But basically, all I want is just this right peak. So let's just say I'm analyzing this data, and you're like, your advisor comes to you and is like, we only care about this one right here. I don't care about anything else. So basically, you want to create a mask, and you want to only use the data right here. That's your goal. So that's your little task. And then I want you to plot the new mask, and then bonus, try and plot your mask over your original data so you can tell the difference. It might sound really confusing. Just give a whack at it, and then we'll come back together. So, yeah. Are we just confused? You can nod your head or you can shake it. It's okay. Yeah, okay. I'll just go over it because we don't have much time left. So let's start with the first thing. Let's practice masking our data. So the first time I heard about this, I was like, oh, that's interesting. But yeah, so we can do this. All right. Pull my notes back up. All right. I'll start. I want a variable called mask. So what I'm going to do, I'm just going to write it out. Maybe you did this a different way. My way is not always correct. All the instructors, our brains all think differently, so whatever works best for you, but this is how I do it. So I'm going to take my data frame, and then I'm going to input my wave column. Now I asked you for, I want everything greater than 13,200. So that's the only data values I want. Cool. Now I'm going to use this AND operator to combine two conditions. So now what I'm going to do is I'm going to have parentheses. Then I'm going to have another parentheses and then df wave. And now I want everything less than 13,700. So that is how you create a mask. Now you know. Cool. All right. So now I asked you to do, don't worry, I'll come back so you can copy it. Now I want you to print the new variable and assign x and y. Oh yeah, here we go. Assign new x and y masked variables. Okay, so there's our mask. Let's print it, see what it looks like. Oop. Wait, just a guess. What do you think it's gonna look like? Unless you already ran it. What does using an operator do? Does anyone remember what using the and or not operator does? Exactly, yeah. Did you already? No, no worries. You remembered it? That's awesome. So yes, and or not create booleans. So basically, on our array, we're putting a boolean mask over our data where we only take the true values. So everything that is false gets cut out. Everything that is true stays. So basically, if I print this, we'll see that everything is false for all of my rows because that's up to like 13,800. If I was to print way more, you would see trues in the middle. But basically, we're just cutting off all of the, not the junk, but all the stuff that we don't want. So that's how you create a mask. It's very useful if you're going to go into upper divisional labs. You'll be masking a lot. So very, very helpful. I wish I knew this when I was in this class. But cool. Maybe they taught it and I just wasn't paying attention. Okay, so X masked. This is our new X variable. I'm going to set it equal to my wave column, but now I add a new bracket called mask. So remember, if we go way back to like lists and indexing, and we use like 0, 1, 2, or you sliced it or you stride it, and you do that horrible homework 3 that everyone always hates. You do the same thing with the mask. So you're doing the true and false, and then we'll do the same thing with Y. So I'll copy that, and then we'll do Y. And then this is flam. Great. Okay, so those are our new variables. Now I think I just ask you to plot it. Yeah, plot only your new masked frame. So now we only want the big peak to the right. So we'll do plt.plot, and then I'll do x masked, whoop, masked, y masked. There we go. And then plt.show. Cool. And there's our big peak. I'll zoom out just a little. That's the only one we wanted. It's at the very edge. If I scroll back up to here, we basically chopped the data right here and right here, so we're only grabbing that one peak. Cool. I'll zoom back in if you want to copy. All right, so does anyone want to see the bonus, or do you actually want to get to Scipy? Raise your hand for bonus. Okay, no bonus. So the bonus was to basically plot your mask over. You can look it in the solutions later. Okay, so now, okay. We don't have time to do this guy right here, so ignore this one. Do not copy this. Ignore that. But copy this function right here. We are creating a Gaussian function. So you're looking at those peaks. They look like they're very sharp. A common mathematical thing that looks like those peaks are called Gaussians. So a Gaussian is basically, if you've seen like a bell curve, same idea. It's just like a thing with like a hump in the middle. that's the function. If you can't see it very well, sorry about that. But that is the shape we're going for, because then our peak looks like this. So you'll see we'll have to like smush our Gaussian quite a bit. We'll have to play around with the parameters, but that is what we are going to be copying for now. Great. Okay, do we have it copied? No, okay. Okay. Um, Now with our last few minutes, I'm gonna leave you with this. I want you to try and use that function. The initial parameters might not be correct because I wasn't having you fit all three at the same time. But just play around with it. And then I want you to see if you can fit it, and then if you can figure out what the parameters are. So it's kind of a lot to do in the last 5 minutes, but last 2 minutes. But I'll give a whack at it. Try your best. I'll post the solutions later, and you're welcome to take a look. But yeah. Okay. So with that, um, here is the engagement. You can fill it out before we're done today. I'll post the solutions if you want to finish up the Scipy curve fitting, and then you'll get a lot of practice on your homework. So hopefully that'll help clear up some ideas. First time I learned Scipy, I was like, oh, this is weird. So yeah, practice really helps. But yeah, great job. And then next week we have AstroPie, my favorite.